Hello everyone, welcome back to my video lecture series on embedded controller laboratories. Today we will see a pulse wave generation using an internal PWM module of LPC1768 and to control its duty cycle. So after going through this session, the students will be able to develop an embedded C program to generate a pulse wave and control its duty cycle using an internal PWM module of LPC1768. So this program or this PWM is mainly applied in LED dimming and servo motor controls. Today we will see LED dimming application with this program. So before going to the program, we should understand all the register set of pulse width modulation. So here the first register of this PWM is TCR register. TCR is time control register. So basically this is used to control the timer counter and preset counter. There are two counters we have here, timer counter and preset counter, prescaler counter. So here it is only bit 0 and bit 1 and bit 3. Only these 3 bits are used out of this TCR register, whereas bit 0 is used to enable and disable TC and PR. TC is timer counter, PR is prescaler counter. So here bit 0, if it is equal to 1, then TC and PR are enabled, and if it is 0, both are disabled. Bit 1, if it is equal to 1, then reset the both TC and PR. So that is for that purpose we are making it as TCR equal to 0x00000002, whereas the bit 1 is equal to 1 here. So that we are resetting time TC and PR. Then bit 2 is not usable, and bit 3 is used to enable PWM mode. So that is output mode. So here we are enabling the PWM 1 output 2. Overall, to enable the outputs of PWM, we are setting the bit 3. So TCR is equal to 0x00000009. Then another register is PR register. So prescale register. So this is basically used to control the resolution of PWM outputs. So in the sense that the output will vary according to the clock cycles, peripheral clock cycles, peak clock. So here we are making it 0. So when we start this PR, so it goes on incrementing by 1 of the timer counter. TC will increment by plus 1 when we start this PR register. So first we are setting it to 0. The third register is PCR register. So basically in this register only the bit number 2 to 6 and 9 to 14 are used. So bits 2 to 6 are used to set a single edge mode or double edge mode, and bits 9 to 14s are used to enable and disable PWM outputs. So that actually we have 6 outputs, 6 channels in this PWM. There are 2 PWM, PWM0 and PWM1. In each PWM there are 6 outputs. So basically we are going to use PWM 1.2. So to control PWM 1.2, 1.3, 1.4, 1.5, 1.6, the bits 2 to 6 are used. So if it is 0, these outputs will be a single edge mode, and if it is 1, these outputs will be having a double edge. Bits 9 to 14 are used to enable or disable PWM outputs. Here we are setting a bit 10. So bit 10 is set to 1, then PWM 1.2 output is enabled, and bit 2 is set to 0, then single edge, we are setting it to single edge, so that we are setting a PCR value is equal to 0x00000400. Then another register is match registers. So there are 6 registers, 6 match registers, MR0 to MR6. So where here we are using MR0 and MR2, which contains a pulse width values. So here MR0 is containing a maximum value 30,000 in a decimal number, and MR2 we are using, MR2 is equal to 0x0000000100, that is 256. Then these registers are controlled by MCR, that is another register is MCR, match control register. So here what will happen is this register is basically used to specify what actually the operation can be done when the values in a particular match register equals to the value in the TC. That is, each MR register is going to function with the 3 bits and 3 functions. If bit 0 is basically of this MCR bit 0 is controlling the function of MR0. So MCR bit 0, 1, 2 are used for MR0. Next 3 bit 3, 4, 5 are used for MR1. 6, 7, 8 are used for MR2, and it goes on. So here bit 0, that is the first bit for MR0 is interrupt. So if it is set to 1, then it will generate an interrupt, or else the interrupt will be disabled by the MR0. So whenever it reaches to a maximum, it should generate the interrupt, or else it will be set to 0 for disabling purpose. Then bit 1 is for reset, and bit 2 is for stop function of same MR0. Then we have IR register, which is interrupt register. So basically we want to enable all the interrupts. So here we are storing the value 0xFF for IR. So IR is equal to 0xFF. So here bits of this IR register 0, 1, 2, 3 and 8, 9, 10. So all these bits are used for MR0 to MR6 respectively, and other bits of this IR registers are reserved. Then another important register is LER, load enable register. So this is a register which is used to control the way where the match registers are updated. So directly the match, if you put some value into the match register, they will not be updated. They have to be uploaded, they have to be updated by using LER register. So here we are putting LER is equal to 0x000000FF. That is, we are enabling all the MR registers, shadow copy registers. So each match register has a corresponding shadow register. That is, MR0 is having another MR0 shadow register, which is a bit of 0 in LER register. So bit 0 is MR0, bit 1 is MR1, bit 2 is MR2, and so on up to 7th bit. So here also these all MR0, MR1 are shadow registers of the original MR registers. So here the value in this shadow register is transferred to the actual match register only when the two conditions are met. So when the PWM1 TC, the timer counter is reset, that is after reset it is going to begin for the next period, and a corresponding bit in the PWM1 LER is equal to 1. So if bit 0 is equal to 1, then whatever the value present in MR0, that will be loaded into MR0 actually. So hence only when these two conditions are satisfied, the value is copied to the original match register. We will see in the next. So beginning with the program, basically in the beginning, hash include LPC17XX dot H file, header file we need to include. Then here we are defining two functions. One is PWM underscore init, initialization init, and another one is duty underscore cycle. So the definition of these two functions we will see it later. Then we are creating two integer values, integer variables I and j, and then unsigned character flag and flag1, two characters. Then starting off with the main program, first of all I will call a PWM underscore init, where I want to initialize all the registers first. That is why I am calling PWM underscore init. Then while 1, that is a forever loop, when I enter into this, a duty underscore cycle, that is I want to vary the duty cycle. So that function I am calling into a while 1 loop. For this duty cycle, there should be a delay so that we could see the degree width of the pulse is going to be varied. To see that variation, we are generating some delay. So that is for j is equal to 0, j is less than or equal to 1000, j plus plus. Now here, let us initialize all the values of the registers of PWM. First, void PWM init underscore init void, starting with the first line of this function, LPC underscore SC pcon p, that is peripheral power control of peripheral. So here PWM1 is going to be powered up first with this value. 1 is shifted to the left side by 6 times. Then LPC underscore pin select, pin configuration, pin select register is used. So basically pin select 7 register is used for port 315 to port 316 to port 331. So out of which we are going to set P3.25. So this P3.25 is basically hardware pin is 27, and this pin is having 4 alternative functions, out of which to choose a fourth alternative function we need to make 000C 0000, where the fourth alternative function is PWM 1.2. That is we are enabling PWM1 function with the output 2. So that is channel 2. So after selecting this, then we are going to set the registers. So as we have seen, the PR prescale register, which is holding a value which is going to be increased, a count frequency. So which is basically a 00000000. We are resetting it. Then PCR to enable, that is to select whether the single edge and double edge, that. So for that, previously we have already discussed this PCR value. Then MCR, this also we have seen. Along with the value we have seen this MR0, MR2, So two registers we are taking here. MR0 register, which is going to contain which contains the total duration of that period, one period, assigned period duration. MR2, which contains that is pulse duration, a single pulse duration, that is width for other match registers. So other match register is nothing but MR0 here. Then LER equal to FF. FF is nothing but whatever the value we are putting here, MR0 and MR2. They are by writing only the values into this, it will not be created. Then first we should load those values into MR0 and MR2 only when LER is equal to FF, that value, a particular corresponding bit is equal to 1. So that is why we are making it as FF. Then TCR, and we are initializing TCR 2 times here. One time reset counter and Prescaler are equal to 0. Then TCR is equal to 9, that is enabling PWM and counter. Then we are calling the duty cycle function after initializing all the values. Now here the MR0 is having a 30,000 value, MR2 is having basically a 256 decimal and 100 in hexadecimal. So here match register, the value of MR2 is going to be loaded into is going to be increased from 256 to maximum 30,000, and this value is putting on the output side that we are using now, PWM 1.2, that is second output we are taking. So we are taking the output from MR2. So as this value changes, the MR2 value changes, the width of on duty cycle is going to be varied, as well as the off duty cycle. So here beginning with this function LPC underscore PWM1 IR, that is interrupt register, we are clearing all the interrupts here, that is equal to FF. If it is FF, all interrupts are cleared. If flag is equal to 0, so now the condition, okay, basically it is going to be 0. So if flag is equal to 0, obviously it will enter into first if condition, LPC underscore PWM1 MR2. So this is pre-increment, MR2 plus equal to 100. So continuously MR2 is now going to be incremented by 100 plus 100. So that is 256 is the decimal number which we have already placed, that is going to be incremented by 100. So it will be 356, 456, 556. So continuously it is going to be increased. This value is going to be loaded in the MR2 only if the two conditions met. So in that we are using one condition here, that is LER is equal to FF 0x FF, sorry 0x 000000 FF. Then the 100 is going to be added into the MR2. Then we are checking whether the MR2 is greater than 27,000 value, because our maximum value is 30,000 which is being loaded into the MR0. So we should not cross that 30,000. That is why we are checking the MR2 value whether it is maximum more than 27,000. If yes, then we are changing the flag status. If it is not, then again the value of MR2 is incremented, then that is going to be updated. So consider that MR2 is connected is actually a PWM 1.2 where we have already enabled the pin number 27, PWM 1.2, PWM1 output 2. So we are sending a value through MR2 register here. So MR2 is now updating towards a plus values, plus 100 every time. Again it will check whether it is more than 27,000. No. that is, it is checking the duty cycle here. Then again plus 100, check whether 20 more than 27, no, again plus 100. So it goes on increasing up to 27,000. Then when it reaches more than 27,000, then it will enter into the if loop. Then if condition. So here flag 1 is equal to FF, flag is equal to FF. Both flags are going to be made FF. Then whatever the value is there, MR2, that is going to be updated through LER. Okay, then after this, now it will check flag whether the flag is equal to 0, 0. No, but now condition is failed. Then it will go to else condition here. So now here else if, there is one more condition, else if flag 1 is equal to FF. Yes, definitely now flag 1 is equal to FF now. Now what will happen? The value of MR2 is already updated with the more than 27,000. Now MR2 value in this else if condition, MR2 value is now decreasing by 100. So that is going to be updated through LER. So one more condition is there, whether the MR2 value is less than 300. So that is duty cycle is less than 1%. So that we are checking. If it is yes, then flag equal to 0 and flag 1 equal to 0. And again update the value with the lowest number of MR2. So this goes on, and the value whatever we are generating on the pin number 27 is going to be increased and decreased with the pulse width. So we will in the next we will see how we are getting the output. Okay, so after burning the hex file into the board, this is a PWM module, Pwm output. So when we connect the probe, CRO probe, positive probe, and the negative probe is connected to the ground. If you connect here, so here the width of the pulse on duty cycle and off duty cycle is going to be here, on time period and off time period.